I'm going to tell us staging a problem. I'm going to start by providing what I feel is a good example of one you've already seen before or similar to what you've already seen before. And I'm going to ask you to come up with the stages that are being left out. So here's this initial setup. All right, so this is what we see at time equals 0. Assume it is a frictionless system. Again, this is t equals 0. Then we have a different condition at the end. So initially the block is at the top of some ramp, and at the end there's this instantaneous moment where the blocks have come to rest. Everybody understand? Can you picture in your head kind of what happened here? Now what I want you to do is I want you to come up with whatever number of stages you need to explain what happened in between. Where the idea here is for us to be able to apply a physics principle to each stage. So when you saw me do this, I broke out stages in the middle, things that I thought would be good stopping points to allow us to apply a physics principle. And I'm not telling you how many stages are in the middle, but we only have a few principles to apply. So you come up with what you think are the middle stages. Get them on your whiteboards and into your notes. We will likely have to make adjustments. I'm going to pick out 2 groups, and their job is to demonstrate to me what they believe the intermediate stages are. So let's go with their stages. They started with t equals 0. Then they have another stage where the block has moved to the bottom of the ramp. So I'm going to just move the block to the bottom of the ramp. And it has some velocity here. And I'm just going to call this T1 to indicate that time has elapsed and it made it to the bottom. Is the velocity of this block going to change as it slides across this ramp or slides across the horizontal surface? All right, so we can just label that V1 and know that's going to be the same until it hits the block. Now, they had another intermediate step. And it had to do with the block contacting the larger block that was at rest. Suggesting that there is a moment just after contact where there's some V final that occurs. We're going to call this T2. Now, they added a couple things, but not much. There's a transition from here to here. Something occurs there. There's a transition from here to here. Something occurs there. And there's a transition from here to here. So there's something that happens from t equals 0 to t1. There's something else that happens from t1 to t2. Something else that happens from t2 to t final. Now, what you're looking for are full transitions. I had a whole bunch of people who have a picture of the block somewhere in the middle of the ramp. The problem is that as long as we're talking about the middle of the ramp, the block is changing. It's not reached some final speed or some final height or some final position. It's transitioning. The end of a stage should be the end of a transition. That's what you're looking for. The reason we picked the bottom of the ramp is because it's no longer speeding up anymore. So it has a constant. Something has happened already to it, and now things are constant. But then something else happens. A transition occurs. Something changes. So your transitions should indicate the end of something happening. Now, as notes go, I believe there are at least 3 things represented here. 3 transitions, specific things that occurred that you could look for in a problem. For example, there was and is a change in height. We look for changes in height. They suggest conservation of energy. Whenever there's a change in height, there's a suggestion of conservation of energy. You should look for changes in height. And these will be things like ramps, roller coasters, objects that are dropped, or thrown. But generally we have mg h minus h naught equals 1/2 mv squared for these kinds of conditions. We set the energy at one point equal to the energy at another. And just a reminder, you could have kinetic energy and a change in height, and you could still have some potential energy after a change in height. But at its absolute, potential energy was converted to kinetic, or kinetic was converted to potential. Like that, we can have the compression of a spring. Now, there can be multiple things for these, but we're trying to bring to bear what's happening in this problem. This suggests conservation of energy again. So spring launchers, or spring stoppers. We look for phrases like max compression of spring. As a phrase that's often used to describe this. Usually an object is moving when this happens, and then it's not moving when the spring is at its maximum compression. We look for one object striking or contacting another. This suggests a collision. These are conservation of momentum. These are the three things that we tended to talk about in this unit, but they show up for a lot of things. Understand that these should be complete transitions. For you to use change in height, the object has to have changed its height and is no longer doing it now. So we wait till it gets to the bottom of the ramp, and that's the end of a transition. If we're doing with the spring, we wait till the spring is all the way compressed. Or if it started compressed, we wait till the spring is all the way relaxed. That's a complete transition. It allows us to compare the two states. Collisions are different though. Collisions are the instantaneous moment before contact and the instantaneous moment after contact. So when dealing with a collision, that's a very small period of time. Especially in this case, because the instantaneous moment after the collision, the two blocks are moving together and immediately start pressing up against a spring. Now, fortunately for you guys, Paradise Falls, they told you all of the things here. So they told you that in this case, mgh equals 1/2 mv1 squared. They told you that occurred. And they're right. During that transition, that's how we figure out how fast the block is going. In the next transition from T1 to T2, there's a collision. The instantaneous moment before the collision, all of the momentum is in the first block. And the instantaneous moment after the collision, all of the momentum is in both blocks. Right? That's the instantaneous moment before the collision and the instantaneous moment after the collision. That's from T1 to T2. And then from T2 to T3, or in this case, T final, the spring is compressing. So you have to be careful here because we do have kinetic energy right after the collision. But both boxes are moving, and they're both being acted on by the spring. Now, drawing this picture for a paragraph length response and writing all this, it's not going to get you the points. But at least you now know what to talk to. You know to talk about this, this, and this. This is what the problem is about. That's not everything, but this is what the problem is about. All right, today we're just staging problems. Let's stage another one. Can you imagine what happened here? Okay. I want you to see if you can stage this problem. What parts did I leave out? So working backwards, there's a moment here where the dart has contacted the block, and both the dart and the block are moving upwards. Right? That's something that they said happened, that there was a collision, and before it started to move upwards, they had a certain amount of velocity, and this would represent conservation of energy. I think that's true. They also talked about the moment before that happens, that there's the part where the dart is just about to hit the block. This is that instantaneous moment before the collision, where it has its initial velocity before hitting the block. All great. I think there's something here that we need. And if not there, then we need to talk about the difference between these two states. Because conservation of momentum will explain this one. And energy explains this one. What explains these two? Anybody want to take a crack at it? Because you could do two different ways. Lance?
Would it be, would you say explain constant?
Well, yeah, that's what David had said. David's thoughts are, we have a point where the dart has acquired velocity and is now moving upwards towards the block.
Oh, so like in between that, you mean?
Yeah, I don't know that we need this one, but it makes reasonable sense that there'd be conservation of energy here to launch the dart. But we still have the fact that there had to be conservation of energy here to indicate that that kinetic energy gets converted into a little bit of potential energy. Right? Now, hear me out, folks. Not every stage is necessarily part of the problem. If we never need to know this velocity, you don't need to worry about that stage. Like if the problem doesn't ask how fast does a dart leave the spring, we might not need this stage. If all we need to know is how fast it strikes the block, we can compare these two stages. Let me get my phone. So again, when looking at these, we're trying to figure out stages where we can break the problem down. I think this is, we'll probably do a little more of this tomorrow, I think.